Hi everyone. In this session, we'll discuss some advanced topics in Verilog, like what is switch level modeling, what are the different tasks and functions that are available in Verilog, and how to define timing and delays in Verilog, and some other contents like user defined primitives. Okay, so these are the contents of this session. First, we'll start with switch level modeling. We'll discuss switch level modeling briefly. Then we'll move to timing and delays that are available in Verilog. Then we'll see what is this user defined primitives. We have already seen Verilog primitives, right? Verilog has some primitives such as AND gate, NOT gate, NAND gate. All these gates are already inbuilt in Verilog, so they are called Verilog primitives. You can define your own primitives. Those we'll call as user defined primitives. In short, we'll call UDPs. So we'll see how to define UDPs and how to use the UDPs in any module and build a complex circuit. Then we'll see what are the different tasks and functions, what is the difference between task and a function, and we'll see with some examples. Okay. So let's start with switch level modeling. We already know that Verilog has 4 level of abstractions. What are those? First one is switch level modeling. Second one is gate level. Third one is data flow. And finally, we have either algorithmic or you can call behavioral, right? We have already seen what is gate level, data flow, and behavioral modeling. Now let's discuss about switch level modeling. Among these 4 abstractions, the switch level modeling is the least abstraction, or you can say lowest abstraction. Why? Because here in switch level modeling, you have more control over your circuit compared to all the other modelings. But the writing complex functions using switch level modeling is difficult because you have to define every design parameter, every design flow in terms of switches, which is a very tedious job. But you should know how to design a complex circuit using a switch level modeling. So it is used to design leaf cell modules using transistors, right? We have seen the top down approach and bottom up approach in the beginning of this course. The top down approach, if you see, if you want to build a 4-bit triple carry adder, what we did, we have used, this is a 4-bit triple carry adder. To design a 4-bit triple carry adder, we have used 4 T flip flops like this, and inside each T flip flop we have a D flip flop and an inverter, right? Each T flip flop is made up of a D flip flop and an inverter. So inside each D flip flop or inside each inverter there will be transistors, or you can say switches. So the switch level modeling is used to define these leaf level modules. These are called leaf level modules, right? So in Verilog, the design capability is with only logic values of 0, 1, X and Z, and it has their own strengths. What I meant here is you can only design digital logics but not analog logics. You cannot have a value between logic 0 and logic 1 like this, because that would be an analog value. In Verilog, you have only digital logics which are 0, 1, X and Z. So there is no analog capability. Thus, the transistor can be used as a switches. Normally, the transistors NMOS and PMOS can be used either for switching operation or for amplification, right? This will use in analog circuits and this will use as a digital circuits. So in Verilog, we have capability of only these 4 logics. So the transistor here is primarily used for switching operations. That's why whenever I say transistor or switch, they both are same. So what are the different elements that are available in switching modeling? Switch modeling, right? So first one is MOS switches or MOS transistors, which are used as switches. And then we have bidirectional switches and power and ground elements, resistive switches. Then we will see how to apply delays to all these switches. So we will see one by one. First of all, what is MOS switch? So a MOS switch is a Verilog primitive This is also a primitive. This is not a user defined primitive. This is a Verilog primitive in which you can define two MOSFETs, either PMOS or NMOS. This is the symbol for PMOS. This is a symbol for NMOS. Okay. Usually the MOSFET terminals will be like this, right? If this is an NMOS, then this is gate, this is drain, this is source. Similarly, if this is PMOS, then again this is gate, drain and source. But here in Verilog, since it is acting as a switch, one of the terminal is data, the other terminal is out, and this terminal is control. Okay. Based on the value of the control signal, the data is either passed to output or it doesn't pass, which is like a switch action, right? This is your control signal. If the control is 1, then switch will be closed and your data, whatever data present here, will be passed to output wire. Similarly, if the control is 0, then switch is open, then your data won't pass to the output. So the same operation we can obtain by using NMOS and PMOS. So the syntax of NMOS and PMOS is, you can write the primitive, this is the keyword, small NMOS, then N1 out, comma data, comma control. So always you have to write the output as the leftmost terminal, then data is your input terminal and control is your control. Okay, you can either give the instance name or not, it is an optional thing. Similarly, I am writing the syntax for PMOS. PMOS, here I am not writing the instance name, I can directly write out, comma data, comma control. So let's say this is N control, this is P control, I am naming them, so I have to give same names, N control, P control. So usually this is a positive logic and this is a negative logic. So in order to have the conduction of data from data to out, your N control should be equal to logic high. If it is logic high, which is logic 1, then the output will be equal to your data. If it is logic low or 0, then your output is in high impedance state. Okay. So that is about NMOS. Similarly for PMOS, if your logic is 0, since it is a negative logic gate or negative logic transistor, if your P control is 0, then output will get the data from data signal, and if your logic is 1, then there is no conduction. Okay. So these are PMOS and NMOS. Let's see the truth table of PMOS and NMOS. So I am drawing a truth table of NMOS, and one side I am drawing data and other side I am taking control signal. Right? These are the two inputs we have. Based on the control signal and based on the data, your output will appear. So what are the possible combinations that data can have? I already told 0, 1, X and Z. We have only 4 level of possible combinations, which are 0, 1, X and Z. Similarly, the control can also be 0, 1, X and Z. So what happens for NMOS is, if the control is 1, then only there will be a data conduction. If the control is 0, then if the control is 0, no matter what is the input data, your output is always in high impedance state, right? So if the control is 0, there is no conduction of this switch, the switch is open, so your output is always in high impedance state. If the control is 1, then your data will appear as it is. If it is 0, then it will appear, your output will be 0. If the data is 1, your output will be 1. If data is X, your output is X. If data is Z, your output will be Z, right? Then we'll see what happens if the control is X. If the control is X, then 0 will be your L. L means here logic low, it can be either 0 or X. Okay. Similarly, if your control is X and your data is 1, then it will be H. H means logic high, which is either 1 or X. If your control is X and data is X, then you will have X. Similarly, control X, data Z, then you will have Z. Same thing if happens if your control is Z also, LH, XZ. So this is the truth table of NMOS. Similarly, we'll draw the truth table of PMOS. So what is this L and Z? This L means logic low, which is either 0 or high impedance state Z. I am writing Z like this or like this, both are same. Okay. Similarly, logic high is either 1 or Z. So now let's draw the truth table of PMOS. So I am drawing truth table of PMOS for my output terminal. This is PMOS, this is data, and this is out. This is P control. This is N control. So we have P control and we have data. We have 4 possible combinations here, also 4 possible combinations. So what is the property of P switch? If your P control is 0, then it will conduct. If your P control is 1, then there is no conduction. In this case, your output, irrespective of the input value or data value, your output is always Z. In this case, your PMOS will act as a switch and it will conduct. On switch, it will conduct whatever data present, it will be conducted to output node. So this will be entirely copied here. Similarly, if the control signal is the X, then we'll have, if data is 0, then low. If data is 1, then high. If data is X, then Z, L, H, X, Z, like this. So this is the truth table of your PMOSFET gate. Similarly, we have one more switch called CMOS switch. What is CMOS? CMOS is a complementary MOS switch in which we have both PMOS and NMOS connected in this fashion. So PMOS and NMOS we have understood. Now we will see what is a CMOS switch. So CMOS switch, its symbol is like this. It has one PMOS and one NMOS connected like this. So this is P control, this is N control. We have data here and output here. So what is the property of CMOS? It will conduct only when P control is 0 and N control is 1, right? Then it will conduct data to output. It won't conduct if your P control is 1 and N control is 0. In that case, your data will be Z. So what is the syntax for CMOS? Not to call the CMOS, you write CMOS. So I'm writing the syntax here. CMOS, you can give either name or you should not. I mean, it is an optional thing. Either you can give the name or not. It depends on you. I'm giving the name of C1. Then you'll have, first you have to write the output terminal, then input terminal, then N control, then P control. So this output will be data only when N control is 1 and P control is 0. Usually the N control and P control are complement to each other. If N control is 1, obviously the P control will be 0. Similarly, if N control is 0, then your P control will be 1. So they are complement to each other and you can write the CMOS with this syntax. The purpose of CMOS switch is it will be useful when you want to design any multiplexer or something similar to that. If you have two different paths and if you want to select one of the path, then you can use a CMOS switch to select whether this path or this path by using the control signal. We'll see when we design a 2:1 multiplexer using CMOS switches. Okay, so you can do the same operation. This is a CMOS, right? You can do the same operation by using two uh, PMOS and NMOS switches like this, because the same circuit can be drawn like this. You have one PMOS and one NMOS, and if you properly connect these nets, let's say these two nets are equals to data and these two nets are equals to output. This is P control and this is N control, right? So if I write NMOS of out comma data comma N control, and PMOS of out, comma data, comma P control. So these two line of codes is equals to writing this single line, because you can see the terminals out is connected like this and data is connected, and you have N control separately for NMOS and P control separately for PMOS. So either you can write two individual NMOS and PMOS, or you can write a single CMOS also. So now let's see what are these bidirectional switches. Till now, what are the switches we have seen? NMOS, PMOS, and CMOS, right? All these three switches are not bidirectional. They will only conduct from drain to source. The data is at drain and output is at source. In all the three cases, it will be like that only. It doesn't have a bidirectional conduction feature. So that's why we have one more element like bidirectional switches, in which the data can be transmitted both from drain to source as well as source to drain. So there are three different kind of bidirectional conduction switches. They are Tran, Tran if 0, Tran if 1. So let's draw the symbol of each one of them. So this is a symbol for Tran. This is shortcut for transmission gate. Similarly, you have Tran if 0. This is control. And you have in out 1 and in out 2. Since both are bidirectional, so I am writing, instead of data and output, I am writing in out 1 and in out 2. It can be either input or output. It can be either input or output. Similarly, we have in out 1 and in out 2. So this is Tran if 0, and this is symbol for Tran if 1. Right? 0 means there is a bubble, 1 means there is no bubble. This is in out 1, this is in out 2, and this is control. So what is the syntax to call the Tran bidirectional gates? To call Tran gate, use the keyword Tran, then you can write directly in out 1 comma in out 2. Similarly for Tran if 0, the keyword is Tran if 0. You have in out 1 comma in out 2 comma control. For Tran if 1 also the syntax is same. The keyword is Tran if 1, in out 1, in out 2 comma control. Okay. So what is the property of Tran if 0? If the control signal is 0, then only in out 1 will be equals to in out 2. If the control signal is 1, then the input data, let's say if the input data is applied at in out 1, it will stay its own state. Then output data, let's say in out 2 is your output, then it will be in high impedance state. Similarly for Tran if 1 case, if control signal is equals to 1, then your in out 1 will be equals to in out 2. If control signal is equals to 0, then input data will stay its own state and output data will be at high impedance state. Okay. Now let's see what is this power and ground elements that are available in switch level modeling. So there are two elements called power and ground, in which you can assign your VDD and your ground of your circuit. So what is the syntax for this? You have to use the keyword supply 1 and supply 0. The supply 1 will be represented for power and supply 0 will be represented for ground. So how to define them? You just need to define your supply 1, and you can write your terminal name. Similarly supply 0, you can write your terminal. Okay, we'll use this once we do some examples, like once we construct inverter, NOR gate, NAND gate, or CMOS latches. Everywhere we'll need to have this power and ground elements. Okay, now let's see what are resistive switches. Till now we are seeing only MOSFET based switches, right? The NMOS or PMOS, these are MOSFET based switches. There are some elements like resistive switches, in which the MOSFET switch can be replaced using a resistive switch. So why do we require resistive switches? What is the purpose of this resistive switch? In MOSFET switch, if your control signal, let's say this is an NMOS switch, and if your N control is 1, then what happens? Your data will be passed to output ideally. There is no any signal strength reduction. But in case of resistive switch, there will be a high source to drain impedance between these two terminals, data and output, right? So your strength of the signal present at the input side will be reduced, which is which is like a real world case. Ideally, your strength won't reduce if your output impedance is low. But in real world circuits, if you design any CMOS circuits, the transistors are not ideal. They have their own output impedances and input impedances and lot of capacitances also. So to emulate this property, we will have resistive switches in which the signal strength will be converted from input to output or down converted from input to output by using resistive switches. So the purpose of these resistive switches is to emulate the real world circuits of MOSFET switches. Okay. So this is the purpose, reduce the strength of the signal passing through them. Okay. So what is the syntax? We will have all the switches. Till now we have seen different switches like NMOS, PMOS, CMOS, Tran, Tran if 0, and Tran if 1, right? These three are bidirectional switch and these three are single direction switch. All these switches can be resistive switches like this. You just need to put a letter R before that keyword, then it will act as a resistive switch. And remaining syntax will be as it is. If you want to call a NMOS resistive switch, write R NMOS, then write output, comma, data, comma, N control. If your N control is 1, then your output will be copied from the data, but the signal strength will be reduced. So we'll see how the signal strengths will look like, the input output signal strength relation will look like. So I'm drawing a table. This is my input strength, let's say input strength. This is my output strength. What I meant by strength is, in Verilog, you can define the strength of any signal like resistor or wire by using different keywords like pull, strong, weak, medium. We have already seen what are strengths in while I am defining the gate level modeling. So the same strengths we'll use here also. If your input data is of supply strength, then if you pass it through a resistive switch, any switch, either NMOS or PMOS or CMOS, any switch, if you are passing through a resistive switch, then its strength will be reduced from supply to pull. Either pull up or pull down, it will be reduced to supply from supply to pull. Similarly, if your strength is strong, it will be reduced to pull. If your strength is pull, then it will be reduced to weak. If it is weak, if the input side strength itself is weak, then it will be reduced to medium. Similarly, if it is large, then also it will reduce to medium. If it is small, same, it will be reduced to medium strength. Similarly, if it is medium, then it will be reduced to small. The order is like this. If it is medium, then it will be reduced to small. Okay. If the input itself is small, then output is again small. If the input is high, then output is high. So this is the strength reduction table of resistive switches. So what I meant is, if you have a VDD strength, let's say supply strength, and if you are passing through normal NMOS, let's say this is normal NMOS, then the output signal that is appearing here, this is my output and this is my data. In this case, it is VDD, which is having a strength of supply 1. So the output here will also have a strength of supply. But the same signal, VDD signal, if you are passing through a resistive switch, this is a normal NMOS switch, but here if you are passing through a rNMOS, in this case, the output is having a strength of pull, not strength of this supply. Okay. So why it is necessary? Because if you connect this circuit to some other circuit, then let's say if this is connected to one more NMOS like this, if this output is connected as a input to one more NMOS like this, let's say this is also RNMOS, then the strength from here to here will be reduced from full to weak. So this is like emulating the real world signals, because we already know in the real world there will be some impedances that are present in the MOSFETs. So obviously your strength will be reduced. The same thing can be obtained by using these resistive switches. Okay. So this is all about resistive switches and different kind of switches. Now we will see how to apply delays for these switches. So uh, we already know there will be three kind of delays. Three ways you can apply delay. One is if you don't apply any delay, then there is no delay present for that MOSFET or switch, whatever. If you apply single delay, then it will be considered as both rise time, fall time as well as turn off time. If you apply two delays, then it will be considered as rise time and fall time, and the turn off time will be considered as minimum of this rise time and fall time. If you apply three delays in the syntax, then it will take as turn off time, rise time, fall time, and turn off time. Okay. So let's see the syntaxes to apply the delays. Let's say I want to apply a delay to NMOS like this. NMOS, if I am applying only hash 5, and then I am writing out comma data comma n control. So what does this mean? This 5 time units is my both TR, TF and T turn off. If I don't apply anything, then there is no delay. It is like ideally passing the input to output. Similarly, if I apply 5 comma 7, in this case the 5 is my rise time, 7 is my fall time, and my turn off time will be minimum of 5 comma 7, which is 5. Similarly, if I apply 5 7 6, in this case the 5 is rise time, 7 is fall time, and 6 is my turn off time. Okay. So these are the syntaxes for NMOS or PMOS or CMOS switches. You can apply like this, and similarly you can apply for RNMOS, RPMOS, and rcmos also. But to uh, but let's see how to give delays for transmission gates, Tran gates, right? Bidirectional gates. In case of bidirectional gates, in case of bidirectional gate, Tran comma rtran cannot have any delay specification, because its prime purpose is to pass the signal as it is without any delay. So where it will be used? It will be used to isolate the buses or signals. So in this case, you cannot specify any delay for Tran or rtran. You can specify delays for Tran if 0, comma Tran if 1, comma rtran if 0, and rtran if 1. In these cases, you can specify the delay. Same like this, if you specify only one delay, then it will be considered as both turn on delay as well as turn off delay. Okay, if you specify two delays, then it will be considered as turn on delay, comma turn off delay. If you don't specify any delay, then it will be like zero delay. Okay, so the syntax is like this: tran hash 3. So it is a one delay. So both turn on delay and turn off delay are 3 times time units. If you specify tran 3 comma 5, then this will be turn off delay and this is turn on delay. Okay. So what I meant by turn on and turn off is what is the amount of delay that is present to pass from out one of the node to other input node. Okay. During turn on, what is the amount? During turn off, what is the amount? So this is how you can specify the delays. You can even specify the pin to pin delay by using specify block. I will discuss this in the coming slides.